Hi, everyone. Thanks for joining the DevCast this month. My name is Jim Crispino. I'm the Senior Director of Developer Evangelism here at Genesys. And I have John Carnell joining me again this month. You may have seen John on some past DevCasts. He will be talking about building resilient apps in Genesys Cloud. Before we get started, I've got a few logistics, as always. So we will attempt for a 10-minute Q&A at the end of the tutorial if John can speak fast enough and get through his content. If you have a question during the webinar, please use the Q&A button at the bottom of your Zoom screen and ask a question in the Q&A section. And we will answer that. I'll try to answer real time while John's talking. And if I can't answer them, we'll hold them up and wait for John to answer them during the Q&A period. Also, this is being recorded. It will be uploaded to our Genesys community YouTube channel. You can get to that channel very easily from our developer website at developer.mypurecloud.com. I realize, John, that is the old link. We've just changed it to developer.genesys.cloud. But the old link works. So if you still
will redirect.
It redirects. So if you go there and go to the video section on there, you'll be able to get to our YouTube channel from that. All right, I will stop sharing. I'm going to turn it over to John now. John, it's all yours.
All right, sounds good. And this is going to be a talk on building resilient applications. It's always one of those disconnects between when I give Jim the initial write-up and when I finish the slides. So you'll see resilience integration patterns, but it's really the exact same topic. So my name is John Carnell. I am a platform architect and team lead for the developer engagement team here at Genesys Cloud. And I got the inspiration to put together this talk after a conversation with one of our other directors who's like, I get a lot of questions, problems that customers who are new to cloud development often run into when they're building out their first set of integrations or trying to build on top of our platform APIs. And I said, it's funny, Chuck, because many of the things that you're describing to me are the exact same problems that we had very early on. And we had, as Genesys Cloud, had to learn to overcome as we were building on the Amazon platform and building our own microservice architecture. On top of it, this topic is really near and dear to my heart because I spent like 8.5 years at a financial services company, working as their integration architect and also being a member of their crit-sit response team. So anytime a system broke that was critical, myself and several other managers would get called. And unfortunately, we got called a lot. So I got to see firsthand kind of some of the challenges associated with resiliency, and then carried those experiences forward as I led a team here at Genesys dealing with one of our tier 0 services, basically a set of services in our edge group that if they went down, the platform, a large part of our platform was down. So very familiar with this topic. It's and have lived through it. So we're going to jump through this. This is going to be a very code heavy talk. So if you're not a developer, I'm just going to tell you up front, or if you're like, I don't do anything with Java, this would not be total interest to me. I still encourage you to say, because a lot of these concepts can be picked up and applied to other languages. So let's go ahead. Let's get started. Jim's going to interrupt me because I am going to be switching back and forth between screens. And if I screw up, he'll let me know. And I'm going to try to get through this as quickly as possible so that we can leave some time for QA. So what we're going to do for the agenda today is we're going to talk about why it's important to consider resiliency up front. And we're going to set up kind of a common problem. It might seem a little contrived, but I run into it all the time answering questions for people. And then we're going to look at 6 resiliency patterns that we've used, and they are pretty much industry standard, and how they can be implemented using Java, Spring Boot, and Resilience4j. Pick these platforms because, one, I'm a Java developer, spent most of my career doing Java work, and so very comfortable working within that. And I know for a lot of the bigger enterprise shops too, Java is very, very common. All right. So let's get right into it. Why does resiliency matter? Well, resiliency matters because a lot of times when people are first dealing with distributed APIs or cloud integration, it's very easy to fall into the mindset that I have my integration, I have these APIs, and all I have to do is call it, right? It's really simple. We call it JSON-based API using HTTP. We got lots of libraries. but writing code is, I would say, 40% of the battle of just doing the implementation, writing code. The other half is really about operationalization and resiliency. And if you don't think about failures up front, you're going to be forced to think about them on the fly when you're having an outage and you're trying to figure out how you're going to survive the outage. So this is, on this slide, you see the very 90,000 foot view of your integration in Genesys Cloud. But under the covers, this is really what those integrations look like. We have literally hundreds of APIs in our Genesys Cloud platform. And what you as a consumer see is our platform API, or you'll sometimes hear us refer to it as our public API. And this guy acts as an API gatekeeper or gateway that is routing to over 200 microservices inside the Genesys Cloud environment. And this isn't that uncommon. This is a very common setup for cloud companies. And inside those 200 microservices, you might have hundreds of instances backed with different compute layers, different data layers, and data technologies, and they're all working together, right? And when everything works great, you'll never even see it. But at any point, you could have a failure and you have to be able to design for it. Now, what's really interesting is I'm kind of pulling back the covers and saying, this is what Genesys Cloud looks like. We have all these microservices, we have all this infrastructure, but I would challenge people to even think about the infrastructure on your end. Think about all the dependencies within your own data centers, within your own business organization, between all the systems you use, and all of a sudden that complexity graph just blows out into a major thing. So when I think about that picture of all of those different infrastructure pieces, the first thing I always tell people is, doesn't matter what you're doing, distributed calls or integration, whether it's a real-time application or it's a batch job you're writing, it is an integration, and you have to kind of plan that at some point or another, it's going to fail. And if you don't take and do some planning and understand the dependencies between all of your components and the cloud vendors you're calling out to, you can set yourself up very much to have cascading failures, because when one piece fails, the other piece fails. And a lot of times they occur in the most unlikely of places. Nobody ever thought, I think it was like a year or two ago, that S3 would go down on Amazon. It's one of their most rock solid services. When that happened to us, I think it was actually 3 years ago, we had stuff that we didn't even know was a major dependency on S3. And we learned a lot of really good lessons from that outage and how we deal with that. The way I also like to look at it, and this is a very, very naive availability calculation, but most of the time when you think about availability calculations at a very, very high level, you take each one of your components, you take their percentage of failing, you times them all together, and that's going to give your total availability. So if I just naively took one of our services within Genesys Cloud, took a look at EC2, I looked these up on the Amazon website, looked at DynamoDB, looked at a Redis caching layer, and I just times them all together. And it's like, if you just look purely at the mathematical calculation, you got 99.87% availability. And I don't care what cloud product you're working with, if you just look at the pure numbers, that's what it's going to come out to. But there's trade-offs, right? You've got all these different components all moving around, but you get a lot of flexibility, you get a lot of scalabilities out there. So while it looks like it might not always be a great thing, with the more pieces you have achieving high availability, you can still combat that by thinking of resiliency up front. So the one thing I always tell people is our goal as engineers, because I still consider myself an engineer, I still write code every day, is not to completely prevent failure. We want to try to prevent failure, but we also have to build for resiliency. And we can do it in one of three ways. Is one, if we detect a problem within our services, fail fast. And failing fast means sending back an error response right away that your code is failing. And that if you detect that there's a situation of failure, don't keep hammering the downstream service that you're using. You can oftentimes exasperate the problem by just continuing to say, okay, I'm going to retry. If you're getting something like a 500 back, that indicates an internal server error. The second thing is fail gracefully. Whenever you have an opportunity, look for areas where you could fall back to other data sources or other means of completing an action for your customers. this is critically important within a call center system, right? And even when I, back in my old life, was working quite a bit with our call center vendors, our call center product and our vendors, is I would tell our business partners, I'm going to design this. I can't eliminate failure, but we can try to keep, when something fails, up running. Would you rather have something completely down, or would you rather have something with just slightly older or wrong information for a little bit longer until we can get the system back up? And the third thing is stop the spread, right? Segregate your API calls into their own thread pools. And we'll cover this a little bit later in our bulkheading pattern, but learn to stop a failure in one part of your organization's IT ecosystem or vendor from spreading to other parts. And a large part of that is really understanding the dependencies that exist between your systems and the components that they consume. I'm going to actually, later on when we're going through our fallback pattern, I'm going to actually show you guys in real life where I even failed to take into account a situation, and it surprised me when I was doing testing. So I thought I'd share it with you and everybody else. So for this talk, we're going to really talk about 6 resiliency patterns. These are not anything I came up with. These are industry standard patterns, and many of you have probably come across them at one point or another. I like to break our resiliency patterns into 2 major groups: transient patterns and proactive. The transient resiliency patterns are there for, hey, I have a slight interruption of service. I know that based on the error code I'm getting from calling an API or interacting with a system, that it's a retriable error. So my solution is to implement these patterns in my own integrations so that I can retry gracefully while at the same time not overwhelming or denial of servicing a downstream vendor. The proactive patterns are ones where you run into an issue and you don't know if you're going to be able to recover from it quickly. The vendor or the service that you're talking to is not giving you an indication via an error code that this is a retriable error. So we're going to walk through all 6 of these patterns. Like I said, it's going to be in Java and Spring Boot and Resilience for J. We're going to look at some of their different implementations. And at the very end, I'll also list out, if you're not a Java shop, I'll list out some of the other frameworks that you can use in other languages to implement some of these features. All right, so let's set up the problem. For this, I've got a simple Spring Boot application that I built that I am going to walk through. It basically just takes a REST endpoint that you're going to pass in a queue name, and you're going to call our queue service to get the ID for that queue name, and you're going to call our queue observations query. And this was based actually on a real world scenario that some people ran into. And what we found is that the developers just kind of were a little bit overly optimistic about, oh, I can just call these distributed APIs as often as I want. And, never really thought about, well, are there rate limits? Are there things that I have to plan for? And what happened is every time they had a call center manager opening the application, they would do 2 calls out to Genesys Cloud. And they do this every 20 seconds because they were trying to update a real-time dashboard. So each open tab with 6 calls per minute per queue that the manager was trying to, the call center manager was trying to manage. And so on average, the contact center manager was looking at 5 queues. So that was 30 calls per minute. And when there were 100 call center managers, a pretty big organization, that could turn into about 3,000 API calls on that one OAuth client at a time. And here's where things got a little insidious is, one, they didn't realize this during testing. They tested it with a small number of users. Everything looked good. They ramped it out very slowly. But then once they started turning it on fully, all of a sudden it just fell over. So we're going to go ahead and we're going to take a look at that. So what I'm going to do is I'm going to start our conversation around the topic of caching. There are definitely times when you have to get the absolute latest and greatest data from any of your cloud providers, including Genesys Cloud. However, a lot of times I encourage people, make sure you take into account caching. If you're going into, if you're calling a service and the data changes only regularly, maybe a minute or 2 apart, high volume call, cache the data. I learned this firsthand myself while I was working early on in our edge config services, our edge edge provisioning services, we did a lot of work with AWS, having to use a lot of the AWS EC2 calls to find out information about a bunch of the various services that we were calling. It all worked great until one day we hit a point where we had so many services, we started running into rate limits. Caching was our solution. Now, from a conceptual level, caching looks simple. But when you think about writing a cache and calling an API and implementing a cache, you've got to ask yourself a couple of questions. What kind of caching model are you going to use? Are you going to do near caching, where you're going to store the data inside the runtime and keep it as close as possible to the call? That works great unless you're trying to cache large amounts of data. And if you lose the instance or you lose your service, that data is gone. You have to reload the cache. Are you going to do far caching, where you keep your data in a remote cache that can survive a service going up and down and gives you much more high scalability, like, for instance, keeping your data in Redis? Or are you going to keep it in a hybrid, where you keep some of your data in near, some of it in far? You also got to look at what kind of eviction policy are you going to use for your cache? What's the velocity of change for caching? If your data's constantly changing, a cache probably isn't going to work, because you're going to be constantly evicting data. But hey, if you've got a couple of minutes of time, why not go ahead and between time in which data is good, why not use a cache? And let me give you kind of a real world example of this. I've got my little simple service that I had set up, and I am going to switch screens. So Jim, let me know if I get the wrong screen. I'm going to do a straight up Python script that I just ran. So I'm going to start my Spring Boot application. We'll get into the code in a moment. Okay. And I've got a Python script that's just hitting my endpoint, and it's hitting it one right after another. And without doing anything at all, what's going to happen is we do 2 calls per every call that I'm making here. And I'm happily humming along at about 0.10 seconds, getting out there. And all of a sudden, because we have 300 calls per minute allowed on a single OAuth client, client token, around the 150th invocation, we're going to suddenly start running into some rate limiting errors. We're going to start getting some 429s. And you can see this here. We're just returning this over and over and over again. Well, if you looked at the code that was being put out there, we're making 2 calls, and one of them is to look up queue information. So why wouldn't I cache that lookup of queue information, particularly if I'm just looking up queue ID? And in this case, I can do something simple like using a near cache. So let's go ahead and look at that code. Now, for this particular cache implementation, I am going to go out and I am going to use a cache implementation called Caffeine. First place I'm going to start is in my pom.xml. All I have to do to implement a near cache with Caffeine is, one, make sure that I include Caffeine in my POM file. So that's pretty simple. This is it right here. And then the next thing I'm going to do is I'm going to go out to my application.yaml, and I'm going to set up a configuration. And I'm going to set it up with 2 different caches. And this is in my application YAML. And I'm going to set both of them to say, hey, these caches can't be bigger than 500 items at a time. But, as you're looking at caching your data, I might have different expiration policies. Queue names don't change that often. So I might want to go out there and keep my queue ID information that I'm returning with 1 call and keep it out there for a day. And on my queue data or my queue call, where I'm actually looking up like observation metrics, and those metrics might change for a particular queue, I might only keep it out there for 60 seconds. Hey, if I get a bunch of calls in within that 60-second window, I'm just going to return them right away. So I've got this all set up out here, and I want a quick walk through the code. And this code's a little bit contrived because I tried to make it very, very explicit. But if you went out to the code, you could see that I'm doing a couple of calls out here. I've got a proxy class that I'm wrapping everything with. I'm doing my Genesys call flow. And after I've set up my queue configuration inside of Spring Boot, it's as simple as taking a class and setting it up with a cacheable tag and putting it on the invocation of the class or on the invocation of my proxy. So what's going to happen is, based upon the name of the cache that I've used and the values that are being passed in, these values are going to be used as a key, and the values are going to be cached after the actual call invocation. And in this particular case where I'm looking up just queue info, it's going to cache it for a day. Otherwise, as I'm looking up calls, we're going to keep it in cache for only a minute. All right. But I tell people this all the time because in reality, people are often falling into the trap. I need my data most up to date. And I'm like, do you? If you have to choose between having an outage and interruption or getting rate limited, is a minute okay? You know, if your calls were a minute behind in terms of data, would that be okay? So let's look at this. I'm going to go ahead. I'm going to restart my script. And I want you guys to see the difference in behavior here. All right, I'm going to go ahead. I'm now going to call an endpoint that's actually going to flow through to those cacheable invocations of my Genesys Cloud API. And I go out there, should be up by now, and you're going to just see it all of a sudden just fly. Because I'm making so many calls in that one little tiny period that I am going out, and the first call took 55 seconds. Because, you know, this is a simulation, I'm just calling the same thing over and over again. It literally never hits my rate limits because I'm never calling the backend API. Really, really simple strategy, but I encourage people to take a look at it because it can save you a lot of headaches. The other thing is realize that you don't have to do this with just our APIs. If I come over here, I'm going to flip back to my screen for my screen a minute. We have seen customers run into a problem where they will build a call flow, and then they'll proceed to use a data action to call a Genesys Cloud API, not realizing that that underlying data action is using an OAuth client that is still restricted by the 300 calls per minute client token. And in this particular case, where we ran into, the customer was basically looking up queue information, looking up metric information, and we ended up just using a data table out there to act as a cache. I'm not going to go through the details of it here, but we do have out on our blog, and Jim, I'm just as guilty. Our old developer center was still up and running at the time, where we actually have a blog post out there where we show you how to take a call flow and a cache and use it to short circuit calls out to Genesys Cloud APIs if you truly don't need the most absolute up-to-date data. All right, so that's caching. Let's go ahead and look at the other one, is retry logic. And I hear this, everybody runs into this as a new developer to Genesys Cloud. They're like, I'm getting retries on my calls. You know, what am I going to do here? Can you raise my limit beyond 300? You know, I thought you said the cloud was scalable, and I'm like, it is, but I've worked with a lot of different cloud providers and cloud infrastructure. Things are scalable, but there still are rate limits. So with the retry pattern, what we're going to do is we're going to go out and actually look to see about retryable exceptions that we can detect, and then retry that call automatically if we see that. Now, with the retry pattern, what we're going to do is we want to look at two things. We want to make sure that we don't retry forever. And so we want to bound our time that we're going to retry either by a count or by a time. And then we have to go and access, we have to have some way of determining what kind of exception is retryable. A 500 HTTP status code should not be considered retryable. A 502, 503, or 504, depending on the circumstances and the vendor you're working with, is retryable. A 429 is retryable. In Genesys Cloud, a 429 is used to indicate a rate limit. The other thing you want to do is you want to look at what kind of framework you're going to use for that retry logic. I'm going to show you guys two examples. Our Java SDK is one of our two SDKs that has automatic retry logic built into it if you turn it on. All of our SDKs turn around, all of our platform APIs, if you get a 429, are going to return a header parameter called retry after, which tells you how long to wait before you retry. Now, if you're working already with a framework like Resiliency, it's going to be a more generic retry framework, and we're going to go through that in the code. It's not going to look and be based on an HTTP status code. So let's go ahead and look at the two different retry pieces of logic out there. The first one is going to be with our Java SDK. I've got a little bit of conceptual logic to kind of explain to you guys how our SDK works. Our Java SDK is really, really simple. By default, the retry logic is turned off. However, when you're initializing the API client, if you set the max retry time per second, that is the total amount of time the SDK will retry if it hits a retryable exception like a 429. We do a little bit different with 502s and 503s and 504s, but the 429 is the most common retry out there. And the way our Java SDK works is it basically says, hey, I know that a 429 is a retry. If I encounter that after calling one of our platform APIs, it will automatically inspect the retry after parameter, and it will wait that number of seconds before trying to call again. The max retry time sec window that's been set up here with this initial property is going to sit there, and it's going to wait up to that total amount of time retrying. So if you set it for 60 seconds and you get 3 retry errors within there, once it gets beyond that 60-second window, it'll basically error out with an API exception. We consider 502s, 503s, and 504s a little bit as retryable, but we don't return a retry after on that. Instead, we sit there and say, we're going to retry, and we're going to let you define or use a default back off logic. So I get my first retry, I'm going to wait 3 seconds. With a 502, 503, or 504, I get my second retry, I'm going to wait 6 seconds. I'm going to wait 9 seconds until I get beyond this window. So let's go ahead and look at just how to activate the retry logic using the Java SDK. It's really, really simple. You basically, when you're initializing your Java SDK, you're going to go out here, you're going to create a retry configuration object. Oh, hold on a minute. I didn't switch my shares. There we go. All right, and we should be able to see code now. Jim, let me know if you can't see code.
Yeah.
So basically, we've got our retry configuration logic here. And what we're going to do is we're going to set our max retry time per second. Because remember, if we don't set that property, by default, our retry logic is turned off. We want to leave that in your control. Because there can be situations like if you're building a real-time integration where you've got a customer sitting there waiting for a response, you might not want to drag out for 10 seconds, 20 seconds, 30 seconds a retry. Instead, you might just want to fail fast and then decide what you're going to do. But if you're using a back-end integration, you might want to turn around and do a retry of 60 seconds, and that back-end can try and it can do the retry after header, look at the retry after header, wait that amount of time. So we've got this all set up now. I'm going to go ahead and restart my Spring Boot application. And I am going to go out there. And this time I'm hitting an endpoint that's specifically set up with our retry logic. And what you're going to see is like what we have seen before. Everything's going to be chugging along, 200 requests per minute, or excuse me, you're getting a 200 back. We're just chugging along. Right about the 150th point, we should be there pretty soon. You're going to see it just stop, and it's going to look like it's hanging. And what's actually happening is the SDK underneath the covers received back 42 seconds on that retry after parameter, and it's now going to sleep for 42 seconds before it retries again. So on that second attempt at the call, if it succeeds, it's great. But if for some reason it got another retry, then it's going to go out and it's going to retry one more time. It's going to get beyond the 60-second window. You get a third retry, it's just going to fail, and you're going to get an API exception. All right, so I'm going to go ahead. We'll let that sit for a minute. But I am going to go ahead and switch our share back because we're going to quick look at a more generic retry framework that a lot of people use, and this is Resilience for J. Now, Resilience for J is a little bit different than the Java SDK, the Genesys Cloud Java SDK. The Resilience for J framework is a general framework, so it doesn't look at HTTP status exceptions right off the bat. Instead, you define what exceptions you consider to be retriable. This is, this is a much more general framework. It's really nice because it can be used for just about any kind of distributed call. And I always tell people this: when you think about your integrations, don't just think about my service calls. You also have to think if you're doing any remote calls on your end to your own databases or your own Redis caches or whatever, you need to look at doing retry logic, circuit breakers, these resiliency patterns. It's not just for distributed calls. So how Resilience for J works is it's a generic framework. it works off based on a number of attempts rather than a specific time window. And after the initial call fails, it's going to look against a configuration list and say, oh, this is one of the exceptions that I'm good with, that I know I can retry on. And so I'm going to retry based on the logic that you set. So you set in your configuration a wait duration, a back off multiplier, and it will just continue backing off until it hits the maximum number of exceptions that have occurred. So what we're going to do is I'm going to turn off our rate limiting logic. We're going to go walk through real quick our retry logic. All right, so I'm going to go turn this off. For resilience for J, you're just going to have to include the resilience for J poem inside of your code. You're going to use resilience for J Spring Boot 2 in Maven. And then what you're going to do is you're going to have to, again, go out to your application.yaml, and resilience for J is going to go out and you set up basically an instance or a profile of how you want to deal with a specific call. One of the difference between our Genesys Cloud Java SDK and resilience for J is our Genesys Cloud SDK applies retry logic at a global level for any HTTP calls coming from the Genesys Cloud SDK. Resilience for J lets you set up different retry profiles and then apply them via an annotation. So in this case, I've set up a profile called Genesys Retry. I'm going to wait 55 seconds on the call, and I'm going to have a maximum of 3 attempts. I'm not going to do an exponential back off. I could set it up to try, double the amount of time between each back off. So it's going to wait. And then the only exception that I'm ever going to retry on is a homegrown exception that I wrote, and which I will go through, called a resiliency exception or a retry exception. So once we've got that set up, it's pretty easy. I'm going to go out here to my retry logic. I had this uncommented out because I didn't want to have 2 different retry packages going at the same time, the Genesys Cloud SDK and ours. But basically, all I'm going to do is just like before with the caches, I'm going to annotate them using a resilience for J annotation, and all I have to do is provide a profile name. So same thing as before, I'm going to go out and I'm going to restart my application. All right. And I'm assuming everybody can see my code, Jim?
Yep.
Okay, perfect. All right, so we're going to hit the retry again, and we should see the same behavior. The first 150 calls, which are doing 2 Genesys Cloud calls underneath the covers, are going to go through just fine, and then we should be hitting a pause. Okay, so we're cooking along. Everything looks great. Everything's good. I know sometimes watching these things can be like watching paint dry. But I often tell my my kids, I'm like, the thing about being a software engineer, oh, that didn't quite work. I'm still getting a 429. Excuse me. I wonder if API client. And now you know it's not a live demo unless something doesn't work. Okay. All right. This still doesn't work. I will take a look at it afterwards, but the code is out in a GitHub repo, and I guarantee you it was working.
Yeah, I'm sure people get the idea, John.
Yeah, I'm sure they do too. All right, so we're going to cruise along. Nope, didn't work. So I'll just have to take a step back and look at what was going on there. All right, so let's go ahead and keep moving on. Apologize for that. Hopefully the rest of my code examples will work. But let's go ahead and switch back, because now we've gotten through the retry pattern. All right. And we're going to talk about the next pattern, which is really, really simple. Timeouts. And what a timeout is it's basically you're making a distributed call and you don't want that call to be unbounded on the amount of time that it's going to wait for failing or to return, because one of the most insidious errors that you can run into in any kind of critical situation is when a service is not down. Those are easy to detect. It's when a service is running slow, because what will happen is if you don't take into account that that service is running slow or could run slow and you don't time out, you're holding up a thread or you're holding up resources, a database connection. And so then what happens is you start getting back pressure in your own integration or your own services. And that can cause a cascading failure because they're insidious. I've been in situations where a slow running database call literally starts backing up one critical service, and then it causes this cascade effect of taking down 4 or 5 other critical services. So what we're going to do is we're going to do a timeout that basically says, if a call takes longer than 5 seconds, we're going to go out and we're just going to throw an error. We're going to basically pop an error and away we go. So we're going to go and use resilience for J again to go and do our timeout. And what we're going to do is we're going to go back to our application.yaml. And we're going to set our timeout to be 5 seconds. By default, almost all Genesys Cloud platform APIs will time out after 12 to 15 seconds. There are some of our APIs that will last longer, but when I was talking with the platform API team, they're like, for the most part, we automatically time out after 12 to 15 seconds because, this is a very high performance environment. We don't want to hold on to threads and essentially what's our API gateway. We don't want to back up customers. So we're going to set our timeout a little bit lower. And what we're going to do is just like before, we're going to set up a default config. We're going to set up a value, an instance value called timeout. We're going to say, use our default configuration. So once we get out there, what I'm going to do is I'm going to go out to my timeout. And in this case, because I'm not using a thread, I'm basically using a future. I'm going to annotate this with the resilience for J time limiter. I have a future that's kicking off. I'm basically supplying an asynchronous return.
And when it switch screens.
Thank you. I knew that was going to happen at least once during our talk.
All right.
All right. So let me back up real quick. This is the configuration for our resilience for J time limiter. We're basically going to time out after 5 seconds. This is how we implement that. We're doing a completable future. We're supplying an asynchronous Java function. And we are sitting there and then saying, use the Genesys timeout with the time limiter annotation. All right, so let's go ahead and run this. I always like to start from the beginning. Oh, and there was one other thing. To simulate a timeout, we're going to use a tool called Chaos Monkey for Spring Boot. And for those of you who have used the Netflix Chaos Monkey tool, it's a way of introducing failures into your environment. What we're going to do is this actually lets you introduce it directly into your Java code. You can turn it on or off, both in a config file or dynamically. And what we're going to do is we've set up Chaos Monkey here. We're going to turn it on. We are going to turn off injecting just random failures of exceptions. And instead, we're going to introduce some latency. All right, so let's go ahead and start that. If everything works correctly, we should see our Chaos Monkey coming up. And what's going to happen is as we're running against it, Chaos Monkey is going to randomly cause some of our calls that we've marked to basically just take longer than 5 seconds. I believe I set it as 10 seconds. So what I'm going to do is I am going to call timeout. That's probably why the retry logic didn't work. So what we're going to see is we're going to see, we got some 200s. Oh, we got a timeout there. And we timed it out. We basically popped the timeout. And you can actually see this, that when I throw an exception, I just grabbed an error and logged it out so you could see the behavior. So I'm sitting here, I'm chugging through these calls, and I'm basically seeing random long-running calls. So this is proving out that my timeout is working correctly. Very, very simple pattern, but it's something that you really need to think about. It's just about putting it in early and upfront. All right. So moving along, I'm going to switch back to my slides. And we're now going to look at circuit breakers. Now, a circuit breaker is a protection on the client end. Basically, remember how I said you want to be able to fail fast? The idea behind a circuit breaker is that if you're calling a downstream service and it's consistently failing, you might want to just fail fast rather than having some and give a specific error message. or as I'll show in a little bit, a specific fallback in the event that the service is failing. And the reason why you want this is because it makes no sense to just keep calling a service over and over and over again if it's failing. Now, the cool thing about a circuit breaker, you got to think about it like a house, an electric box in a house. If too much power comes in and hits that circuit breaker, you're basically going to pop it and not let that power go out to the rest of the electrical system in the house. That way you don't burn out your outlets, you don't cause problems with any of your electronics. It's conceptually the same thing here. You're going to fail fast. Let's say you get X number of calls in a row that are failing. You're going to fail fast. You're going to pop the circuit breaker. But the other principle that you want to do with a circuit breaker is let a few calls through over time to see if the condition has resolved itself, because you want to be able to self-heal. All right. Sometimes you're having a problem with the downstream service or remote provider. Yeah, you're going to see a failure. You're going to want to, fail fast, do something with it, maybe go to an alternative data source. But you also don't want to get to a point where you have to recycle your servers or recycle your connections, because you want to let calls through and just try things out. And if everything's good, let's say a half hour later, things have resolved, your system's still back up and running and taking calls. Now, the way a circuit breaker works is something like this. You start getting your first error message back. The circuit breaker that is being put in front of those calls is going to say, have the minimum number of requests failed? Yes. Okay. Maybe it's only one request. Have you reached the error threshold where you're not going to let any more calls through to the downstream system? This should be a yes down here, right? If it's been yes, the circuit breaker is going to pop. Sorry, it's a little confusing because this goes over here. Have minimum number of requests failed? No. We're going to go through. Let's say the minimum number of requests have failed, but you have an error threshold. If it's yes, you're going to pop the circuit breaker. Now you're going to start returning calls. Any calls going out to that downstream service are going to fail automatically. So what's going to happen then is during a certain time window or a number of counts on your circuit breaker configuration, it's going to occasionally let calls through. And if a call goes through and says, hey, are we still seeing problems with that remote service call? You're going to go yes, and you're just going to keep sitting in that open state. All right. And if you have a fallback, which I'll get into, if you get an error, you'll fall back to another piece of code, maybe look up against the cache, look up against the database, or you'll just return an error. But if the problem's occurred, you're going to let the circuit breaker close back, and you're going to let calls still keep going through. So let's look at a circuit breaker using Resilience for J. All right, so what we've done here is we've got our circuit breaker, and I've set up two different configurations. This one we're going to get to in a minute. This is a circuit breaker without with a fallback. This is just, I wanted to show what it looks like with a circuit breaker on, but with no fallback. We're going to make your circuit breaker time-based. Resilience for J can look at, hey, if I start seeing errors, I'm going to wait over a certain period of time, or it can look at a counter-based solution. It's going to wait for 10 seconds in an open state before it tries again, and it's going to look at about a 10% failure rate on our calls. So what's going to happen is when we go out to our circuit breaker then, or when we want to go and protect a piece of code with circuit breaker, we're going to basically just wrapper it with this annotation, with a circuit breaker annotation and the name of the circuit breaker. So once we get past a certain threshold, what's going to happen is we're going to just start returning exceptions, and we're going to start returning a 500, but we're never going to let that call through to the downstream system. Jim, did I switch my code? I did.
Yeah,
good.
You're showing your code.
Okay, good. For a minute, you look like, he's not he's good. All right, so let's go ahead and let's go through our problem again. I'm going to go ahead. Oh, one other thing. I'm going to use Chaos Monkey again. And this time, I am going to change this from a latency-based exception to a true exception, or an exception's active, which means Chaos Monkey is going to actively throw errors into whenever I'm trying to call my remote service. All right. So this time I'm not introducing latency. I could do both, but what I'm going to do is I'm going to run Spring Boot, and I'm going to run, I think it's circuit breaker. Okay, so you can see we're starting to inject some random errors, but we're never quite getting enough that's causing problems. So our circuit breaker isn't popping open on a regular basis. All right, so what I'm going to do is I'm going to go out here and I am going to let this. Now, here's what happened. We got 429s at that issue. It's being covered up because we got a 500, but we finally started hitting enough errors where we got a 429 and we let things through. And so it literally, you see them, hey, here's a bunch of 429s, right? And the circuit breaker basically popped open. We're now just returning 500s and we're not letting any other calls through to our Genesys Cloud services because too many exceptions have occurred. All right. So let's go out now. I'm going to reshare my screen. We're going to go into our next pattern. And this is a circuit breaker with a fallback. And fallbacks are probably one of the coolest things that you can have because you're basically saying, and you can use a fallback with more than just a circuit breaker. You're basically saying, if I run into an error condition on a remote system, maybe I go get my data from another place. Maybe I use a hard-coded list of data that's being returned. Maybe I take cache data and look in the cache. It might not be the most up-to-date data, but basically what happens with a fallback is you're saying an error condition has occurred. You can do a fallback with either a retry or a circuit breaker, but basically your fallback is an alternative code path. So to set up our fallback, you're not actually going to change anything different in your circuit breaker code. I just set this up so I could set up a separate fallback and a separate piece of code. But instead, what you're going to do is you're going to use your circuit breaker, but for one specific call, the call that does the observation metrics, I'm going to go back and I am going to define a function here with this fallback method, and I'm going to take some action. And the big change I made in this code is every time I go look up Q observation metrics, I always shove that data into a hash map. You know, I could use my my caffeine queue, but I just chose to keep it simple. I shove it into a hash map with the last value that was retrieved from that API call. So if I ever run into any problems, this fallback is going to be invoked, and I'm then going to go out and I'm going to pull the value out of the cache. All right. So what should happen is the caller, he will never see an error. All right. He'll get a 200 back because the fallback is going to be invoked. It's going to get the data out of the cache, even though there was a failure out to the Genesys Cloud API. So let's go ahead. We're still doing Chaos Monkey.
You got to switch to your code.
Thank you. Oh, did I not do that? Okay. So here's the code I was just talking about. Thank you for keeping me honest, Jim. Here's my fallback designation within my circuit breaker. I'm basically falling back to this method call over here, and I'm reading my data out of a cache. Every time I had been looking up that data, I turned around and I put it into a hash map, a concurrent hash map. And basically, I'm just reading the data out of it. All right. So let's go ahead. We had restarted that code, and we're still running with intermittent exceptions being thrown. And this time, I am going to go into my fallback. And so what's happening is underneath the covers, we're still seeing errors. You can't really see it unless you go back here. You're seeing I'm actually having Chaos Monkey getting an exception, and then I'm hitting my fallback. Yep. Were you able to see that? Jimmy had a question?
Yeah, that's cool.
Okay, but wait a second. Why did I start getting this error? I mean, everything was falling back and everything was good. Why all of a sudden did I get this error? And I purposely kept this in here because it illustrated a great point, is that when you think about things like circuit breakers, retries, any of these resiliency patterns, you have to look at the entire call chain and all the dependencies involved. Because if you don't, you can think you're protecting your service and you forget about one part of the call chain where you're making a remote call and it fails. And so what happened in this particular case is you can actually go out here and everything's going along, everything's flying. And all of a sudden I saw a bunch of 429s. And for the longest time, I'm like, why am I getting these 429s? It should have just fallen back to the circuit breaker. But remember, I'm making 2 calls, and I only created a fallback method on one of my 2 calls. My first call went and looked up the ID of the name, but I never set a fallback. I never did anything with it. My second call was the one where I had the fallback and the circuit breaker. So eventually I got to a point where I was doing so many calls, I eventually hit a point where I was getting 429 on my API calls. I'm getting a rate limit, but I had no fallback. So the circuit breaker detected that, popped open. So even though I thought I was protected, I wasn't. I bring this up because it points an important lesson that you have to go out and understand all the parts of your call chain. Anything that's a distributed call is something that is a candidate for using these resiliency patterns. Now, the way around this is I could have either put a fallback in here, or I could turn around and I could combine both the circuit breaker with a fallback on the one and retry on the other, and then basically be able to run it. I'm not going to go through it now because I'm starting to come up on time, and I want to finish out and at least give some QA time. So I'm going to switch back. Just a couple of things real quick. There was one other pattern we're not going to get a chance to look at or run in code, but I'll cover it, is the bulkhead. A bulkhead is particularly important when you're working in an environment where you might have multiple API calls. Let's say you're doing a service on your end in your data center that's making multiple API calls, and you want to partition out those API calls into their own thread pools. Particularly, I find this if you're making multiple API calls, or if you're doing it against multiple cloud vendors with 2 very different business functions, you might want to segregate out into separate thread pools those calls. Because then if one partner, one cloud provider, one distributed call is having problems, the other parts of your application can still keep up and running. All right. Because what we're going for is not preventing all failures. What we're going for is trying to keep the application alive and the application to degrade gracefully. All right. Because if you don't do that, it's better to have parts of your app working than none at all, right? To be completely down. So a bulkhead pattern basically in Resilience for J would basically say, hey, I'm going to use, I think by default, I use a semaphore here. I'm going to allow a maximum of 100 calls if I don't declare anything. I'm going to set up. I didn't switch my screen. Thank you, Jim. I'm in here. I'm in my application.yaml. By default, I'm only going to allow 100 calls maximum on any of my calls protected by a Resilience for J bulkhead. I can set up, though, individual bulkheads by API calls. So maybe I want to let one particular API call in my application have more throughput. But once I hit that maximum and I don't have any more available threads, I can either have the API call fail, or I can just have it back up for a bit before it fails. But again, it's the same thing. Resilience for J, you can either create these things via code, or you can basically go out, excuse me, and you can include it as a bulkhead saying, hey, I'm going to use a bulkhead. This is the profile. And then any calls that are part of that bulkhead will share that single pool of maximum threads that they're allowed to take. This is really, really important. I can't tell you the number of times, particularly in my old job, where you might be pulling from 2 or 3 different vendors to carry out an action within your application. And if you didn't bulkhead your application into multiple individual components with their own thread pools, you could take down the entire container and basically crash your app. Versus with a bulkhead, you could only take down part of your app and you could still leave other parts of it up and running. All right, so we're wrapping up. The last thing was really some closing thoughts. Is one, you really have to think about your usage patterns. You just can't slap these integration patterns wherever you go on your services. You have to understand how your users and your applications consume data. You got a back-end integration job where you can wait. You're running a nightly batch job. It can wait on a retry, right? It can wait 60 seconds. You know, you got a front-end app with thousands of users hitting it. You can't wait on a retry. You might have to do just a fail fast and look at an alternative data source. The second thing is look at your failure modes. Look at the entire call. Don't just look at your one problem area that you might have had, or where you think there's going to have a problem, really walk through the entire chain from top to bottom, from when the API call begins all the way to the end. And then also look for those opportunities to grade gracefully. You know, it's all about framing the problem sometimes with our business partners is, do you want the app completely down, or are you okay with getting some data from someplace else? All right, so a couple of additional resources. First and foremost, my favorite book on the subject is Release It by Michael Nygaard. He is like the godfather of resiliency patterns. All of our resiliency patterns, everything you looked at here is out in our GitHub repo. And then because I'm one not to shamelessly self-promote, the second edition of my Spring Microservices in Action book just got released. It's in print in June, but we actually cover resilience for J in one of the chapters, along with a number of other microservices technologies. And I kid you not, I was not planning this, but we're doing a deal tomorrow. I just heard from Manning where the book and a number of other Spring books are available at 45% off. So I just threw the link out there at manning.com, DOTD. But second edition of the book deals specifically with every one of the resilience patterns that we've kind of talked about in here. The other thing I promise is there are other patterns. Poly is a .NET resiliency framework that implements a lot of these. Go has Go Resilience. Node has Cockatiel. And if you're a Kubernetes shop, I'm sure most of you have heard of Istio. Istio is very cool. It lets you implement these patterns completely outside of your service, basically as kind of a sidecar. So as it's coming in, it checks and it does all the things that we just showed here, and it's for its patterns, and won't even let it hit your service if any of these particular patterns get fired off. All right, so I'm going to leave it at that. I'm sorry if it went a little long, but hopefully you can stay. I can stay as long as people would like to answer any questions.
Yeah, thanks for that, John. That was really informative. I think it's cool to see how other people code and the tools they use, and the patterns were really, really awesome. If you have a question, please put it in the Q&A. I realize we're right up against the hour. If you have to go, we understand that. John and I will hang on for a few more minutes. Otherwise, this video will be available out on our YouTube channel.
Great.
All right. Well, we're not getting any questions. So, John, you must have done a fantastic job.
Everybody's asleep, Jim.
Even though it wasn't about a specific API in our set, it was nice to see how to use our APIs and make your own code resilient and not clobber our cloud as well. So.
And I welcome questions. If you guys have questions about these, please post them to the forum too. Like I said, this is out on our GitHub MyPureCloud repo, so you can download the code and you look at it. I'll guarantee you it's not perfect code. It's an example code, but I'm hoping it will get you guys started in your own resiliency journey.
All right. Well, with that, I'm going to close the webinar. Thanks, everyone, for joining. We'll see you next month where we're going to talk about our new open messaging API. See you then. Bye-bye.